Hello, I'm Craig Jones. I want to talk to you for a brief moment about what made me decide to get involved in the engine business. It really isn't something that I specifically planned on doing, but I've had a few other inventions, and I wanted to have a new engine that would be able to power a race boat that I was involved in. And so my concept was to really develop something that would be better than the current internal combustion engines in almost every way, in every way, shape, and form. And it sounds kind of crazy, but if you think about it, the current internal combustion engine, it takes fuel and gas and mixes it in a chamber, compresses it, creates an explosion, and as that piston moves down, it turns a crankshaft. If you think about a crankshaft like a bolt, let's say you're trying to turn a bolt to get a job done, whatever it is, and you understand that to turn that bolt, you would never take your ratchet at the top and jump up and down on the ratchet to turn the bolt. Where the bolt would start turning, you would start moving it. You wouldn't do that. You take the ratchet and perpendicular, one-to-one with the bolt, you turn the bolt. And you realize that the further you go out, the easier it is to turn that same bolt. And so every time you double that distance, you end up getting much more torque. You get double the torque for the same amount of force. So if we had a certain amount of fuel, we mixed it with oxygen, we created the same combustion force, and you doubled the distance, you would have double the torque for free. So the whole idea is to actually have a better leverage distance that will suffice and create more torque than you would otherwise normally achieve. And that's really what the Jones engine did. If you were to take an inline four-cylinder engine, for instance, and create and take 14 parts of oxygen and 1 part of fuel, regardless of what kind of fuel, compress it, spark it, get an explosion and move down, you start at 12 o'clock position at the top dead center, and as the piston moves down, it's turning a crankshaft like this. So it starts up here and it pushes it at 12 o'clock. It goes to 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock. At 6 o'clock, when that piston has gone all the way down, it's at the end of its stroke. So when force, which is down, times distance equals torque, at 12 o'clock, you have no distance. So at top dead center, when the explosion takes place, you have no torque position whatsoever. At 1 o'clock, you have as much as you have at 1 o'clock. 2 o'clock, 3 o'clock is your maximum lever distance. Force times your maximum lever distance is torque. Then it starts reducing down at 4 o'clock, 5 o'clock, 6 o'clock. That's the reason why you have torque curves in engines. If you could take the same amount of fuel and get that extra lever distance, you would have more torque for free. And that's really what the Jones engine's all about. The reality is your average lever distance on an internal combustion engine is about 25% of the stroke. So if the stroke is approximately 4 inches long, you're only going to have an average lever distance of 1 inch. If that engine was a 4-cylinder, 2-liter engine, and you were to take a Jones engine, 4-cylinder, 2-liter engine, I would have about 4 to 5 times the lever distance. So that means I would have 4 to 5 times the amount of torque for the same amount of fuel and oxygen. And that's what it's all about. It's all about torque. And if you can achieve the most amount of torque out of fuel, you have the most efficient engine. I'll explain that in a second, why torque is more important than horsepower. And the Jones engine has that torque position because as it burns, it's burning perpendicular to the crankshaft, just like a ratchet would. As far from the center of the crankshaft as you can possibly go in a single package application. So theoretically speaking, you can't achieve any more efficient application of forces on a crankshaft than is applied in the Jones engine application. we're applying these forces perpendicular, 1-to-1, with a ratio of the crankshaft as far from the crankshaft as possible in any kind of packaging that we desire to achieve, any kind of 4-cylinder, 6-cylinder, 8-cylinder, whatever we decide in our packaging. So, how would any other competitive internal combustion engine be able to compare with ours? Well, the answer is it couldn't. If they're not taking the gas in a combustion cycle of fuel and oxygen, burning it, combusting it, applying the forces direct, 1-to-1 with the crankshaft, as far from the center of the crankshaft, and with forces perpendicular, they can never, with the same amount of fuel, achieve what we can achieve with the Jones engine. The Jones engine takes the maximum force and takes that maximum force and applies all that force to turning that crankshaft. Whereas in other internal combustion engines, take that entire force and slam it straight down on the top of the crankshaft, making the crankshaft turn, and then indirectly applying that force all the way around at different distances. 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock. Remember, all your forces are at the very beginning. The most amount of forces are at the top of the explosion. And so you want to remember that you want all of that at the beginning of the cycle, when the piston's going up and compressing the fuel and the oxygen and it creates the explosion. You don't want that with 0 lever distance. That's why you have to have certain RPMs to generate a torque position for any normal internal combustion engine. I'll explain why. Because an engine operates in an RPMs, that means the amount of burns taking place in that engine, and therefore the amount of revolutions per minute on the crankshaft. Well, the faster it goes, the faster the inertial forces take place, and as it gets up to the top dead center, the spark ignites and the piston starts moving down as a result of the inertial forces, and because the RPMs are moving it so fast, it becomes, once the burn takes place, you're already at 1 o'clock or 2 o'clock position, and so you're maximizing your lever distance when the force is applied to it. See, with the Jones engine, you don't have any of that. The second you start the engine and push the accelerator, you have maximum RPM or maximum torque at any RPM. Now, what does that mean to anybody that doesn't really understand engines? It means if you want to do work with your engine, whether you're driving a boat, a plane, a train, a car, a truck, a tractor, anything, what you want is torque, so that when you push your accelerator, you move the object or do whatever it is you want to do. You don't want to have to burn so many cycles to get to an RPM level so that you can start creating the torque to do the work. You want to be able to get the torque, do the work, and burn it as many times as is necessary to accomplish that work in an efficient manner, or as fast as you want to achieve it. Our engines are backwards. You have to burn, you have to create a combustion cycle faster, burning more fuel to get the RPMs to a certain level, to be able to create the torque to do the work. And so what do we talk about when we talk about conventional engines? We talk about horsepower. Horsepower is nothing more than the amount of burns necessary to do the work. And work is done by torque. So torque is everything. And the Jones engine, the torque is there all the time. So you don't need all of the RPMs. Do you think your tire spins at 5,500 RPMs when the engine's spinning at 5,500 RPMs? No. The engine has to spin at that kind of RPM to generate the torque position and the horsepower necessary to maintain whatever work you're trying to do. But then it's geared down. And those forces are applied through a transmission or a reduction gear to apply to a prop or a tire or to whatever it is that you're working on. With the Jones engine, we have about 5 times. With the Jones engine, we have 5 times less RPMs than the conventional engine. You don't want a lot of RPMs and then reduce the RPMs to do the work. You want the minimum RPMs, and if you need to do faster work, you burn it more often or you gear it up. You don't want to have to gear down because then you're wasting fuel to achieve something simple that you can achieve with the Jones engine. Wouldn't you love to have an engine that you could start, you push your accelerator, you're now burning at 100 RPMs, and you have maximum torque. You want to go faster? Push the accelerator faster. See, in your current car, if you want to pull your trailer or anything, you have to push the accelerator, the torque converter kicks in, brings the RPMs to whatever level it needs to be able to engage and start moving forward. As you keep the brake pedal, the accelerator down, you see that you're starting to rush forward faster as you go faster. That's because the RPMs are getting up to a higher level. You're getting in your torque curve. Now you're creating the torque. Now you're doing the work. With the Jones engine, the second you push it, you have a linear torque curve. You always have maximum torque. The second you push the accelerator, maximum torque. So no matter what, with the Jones engine, you have the maximum amount of work coming out of that fuel. That is the single most important mechanical advantage of the Jones engine over any and all other internal combustion engines, which makes the Jones engine better than any and all internal combustion engines that are out in the marketplace. And the reason it is because the internal combustion engine is what it is. It simply creates an explosion and applies forces to a crankshaft. It's that turning crankshaft that does all the work. If you're not applying forces correctly, you can never compete with something that is applying the forces correctly. That's the primary advantage of the Jones engine over all engines. Why do you think electrical motors are such high torque efficient engines? Because as you accelerate, you have all that electromagnetic array at the outside as far from the center of the shaft as possible. All the electrical energy is as far out as possible from the center. It creates a maximum amount of torque. It's a linear torque curve from the second you engage it. That's why diesel locomotives, that's why cruise ships and very high torque vehicles use diesel electric engines. They use the diesel engine because it's the most efficient to power a generator and to run the electric engine, which is the most efficient engine. What we're doing with the Jones engine is we're creating a perfect internal combustion engine to operate just like an electrical engine. That's the primary advantage of the Jones engine. It's unprecedented, unequaled mechanical advantage. Now, is there any other engines out there that turn in a circle? Yes, there are. The Wankel rotary motor is one of them. But just because it goes in a circle and uses good inertial forces like the Jones engine doesn't mean it's a Jones engine. It doesn't have a good combustion chamber. It doesn't have a good torque position. Therefore, the only way to generate any good power is to spin it often, a lot, at high RPMs, and get into a torque curve at very high RPMs. And that's why the Wankel is really not an efficient engine.